Hi there, it's Matt Heffernan. Welcome back to my channel. I know it's been a while since I've had a video out that wasn't the podcast, and we'll talk a bit more about that later. But what I also did right before the podcast, it was the introduction of my new 8-bit architecture that I'm calling ROCKET88, and of course that was now over a month ago. And it seems like my channel has been kind of dead. I haven't been putting out any of my normal content. Even the podcast was a full month after that last ROCKET88 video. But I do have a lot of stuff that I'm working on just right now, trying to get stuff out that is worthwhile. And I think at this point now, I have some more work done on ROCKET88 that's ready to share on YouTube. And it's basically how I am currently in the middle of the preliminary design of the ROCKET88. We're not really at the point yet where I would say the preliminary design is done. There's still, I think, a lot of high level decisions that are still left to be made, and then we're going to get down into the actual nuts and bolts of getting this virtual processor created. And it's, of course, going to exist as both a Verilog version to run on an FPGA, and then there will be an emulator for it, and that will run anywhere. And that's going to be kind of the point, is that we'll have a very simple architecture that is open source and portable. And that's what we're going to do. But first, I wanted to address some questions and concerns that people had about the name ROCKET88. Well, I'd like to announce now that there is a official backronym for ROCKET88. It stands for Retro Obsolete Computational Kernel for Electronic Transacting. And it has an 8-bit external data bus and an 8-bit internal data bus, thus the 88 after it. But of course, I didn't invent the term ROCKET88. There's a story to it. And originally, the ROCKET88 referred to an Oldsmobile, and it had a V8 engine that Oldsmobile and the GM overlords there called the Rocket, because it was supposed to be a fast V8 engine to put in what was at that point a mid-sized car. And it became very popular. Oldsmobile was never the most popular brand under GM, and of course it doesn't exist anymore, but they kept making the 88 with that Rocket V8 engine all the way up until 1991. There's a so you see a 49 Rocket 88 and a 91 Rocket 88. It was never like the big seller. It was never a real flagship item for GM, but it had popularity for within certain communities, and because it was effectively like the cheapest sort of V8 sedan that you could buy. And of course, that went a long way. People didn't have a lot of money, but they still wanted to have a comfortable, powerful ride. And unfortunately, the 88 kept going, but it was no longer a Rocket 88 after 91. They replaced it with the workhorse of GM at that period, which was the 3800 V6. Of course, that was created by Buick. I myself had a Buick LeSabre with a 3800. You couldn't kill that thing. And but you could definitely kill those old Rocket V8s. And so they went with a more fuel efficient and dependable engine for the 88, but the 88 didn't last that long. Once it became a V6, it just became an oversized, underpowered sedan that basically nobody wanted to buy. And by 99, the end was near. That was it for the Oldsmobile 88. In fact, Oldsmobile itself did not last very long. Oldsmobile didn't even make it until the crash and bankruptcy of GM. That brand had been killed long before that. But it doesn't end there. the Rocket 88, why I chose Rocket 88 was not because I'm a big fan of Oldsmobiles necessarily, but I am a fan of classic R&B and rock and roll. And I think the very important transition point between classic R&B to the beginning of rock and roll can really, the pivotal record is called Rocket 88 by Jackie Brenston and his Delta Cats. And there's Jackie right there. He was a sax player and a singer. And he, according to the album, or not the album, it looks like an album. This is actually such an old record. It came out in 1951, and it came out on a 78 because 45s weren't really a thing yet. That's how old this was. It really predates anything that we consider definitively to be rock and roll. But the sound of the record was harder, more aggressive, and importantly, more distorted than anything that you would have heard before. And that was because Jackie Brenston and his Delta Cats, which actually was Ike Turner and the Kings of Rhythm. They didn't record this record under their own name. They went and recorded it at Sun Records with Sam Phillips producing it. Of course, Chess was distributing Sun Records at the time, so it was sold as a Chess record, but it was really a Sun Records product. And they were already fairly well known among the black club circuit, the Chitlin circuit as they called it then, which had a good following of what was then considered jump blues slash early R&B, and Ike Turner's guitar player had a broken amp, but they wanted to play this song really aggressively, really get the power of singing about this impressive Rocket 88 car, which was very popular with the African American community throughout the lifespan of that vehicle. And that hard guitar playing on a broken amp, it created that fuzz distortion that became the hallmark of rock and roll. And of course, it didn't hurt that rock who was right there in the title. And of course, rock songs from then on, especially through the early 60s, always like to use cars as sort of a stand-in for sexual prowess. So it's like, hey, baby, come take a ride in my Rocket 88. And, it's you can connect the dots there. And that's where Rocket 88 is. And for some reason, when I said I'm creating a processor, a virtual processor called the Rocket 88. He was like, oh, 88. Well, that's there's some unsavory characters out there that want to claim 88, and they're going to think that you're one of these evil people because you're called it the Rocket 88. It's like, no, I'm honoring the legacy of rock and roll and Americana and all this other stuff, things that I enjoy, and the significance of the number 88. I'm sorry, I'm not about to surrender a number to the worst people in the world. The folks who end up surrendering like that, it doesn't turn out well for them. Right? I'm not going to be the Vichy government version of a retro YouTube channel. So let's just continue on to where we're actually at with my Rocket 88. And so here is an extremely simplified look at the components that are going to be implemented within the Rocket 88 core. So, of course, there's going to be externally a 16-bit address bus and an 8-bit data bus. And, we're not looking at having any sort of special I/O addressing like you would have, say, in a Z80. Everything would be just mapped to the memory, just to keep it simple. One address bus, one, read and write line for the whole bus, anywhere on there. We're not creating something that needs to be it needs to work with any off-the-shelf hardware components. It's all software, effectively. And so what I'm going to implement is a basic memory controller that will be able to, within it, have a current address value that it is going to put to the address bus. So it's always writing to that address bus a 16-bit address to fetch or perhaps write to, and then of course external logic will determine what that 16-bit address actually resolves to, if that's RAM or ROM or a device or whatever. As far as the CPU core goes, it doesn't care. And then the data bus, of course, will be bidirectional. So we're going to be either reading or writing 8 bits in parallel on that external data bus. And that's what the memory controller will do. It's like we're going to tell it, depending on the state of the processor, whether it's reading or writing, and what that address is that it's going to be dealing with. And then we're going to take, if we're reading value from memory, we are going to put that value onto the internal data bus. And that's what we can see here. That is also 8 bits. And then that internal data bus will be available to the rest of the components in there. And of course, it is also going to be bidirectional because we're going to be feeding data back to the memory controller, especially for when we want to write that an 8-bit value out to memory. And of course, all reads and writes are going to be 8 bits at a time, just by the nature of this processor. And again, just to keep it simple. And so now we have a bunch of registers. There's certain registers are going to provide addresses to the memory controller for accessing memory. And then it will also provide register values to the arithmetic. I always want to pronounce arithmetic as an adjective, and I think for some reason that needs to be a different pronunciation. I'm going to say arithmetic instead of arithmetic, but you know what I mean. So the ALU, which does all the arithmetic and logic type calculations, those are for binary operations, are going to, could take 2 register values, or it could take a register value on the left side and then a value off the data bus for the right side. Or if it's unary, it is only taking one or the other. And then the output of the ALU, once it does its operation, gets fed back onto the data bus, and that's where it can be written back to a register or written back out to memory, or whatever it's going to do. And then also the instruction decoder will then determine what it's going to do next. And it's really going to be the heart of the system, where it is controlling the registers, controlling the ALU, controlling the memory controller. It is in charge of the whole operation, and is going to tell the memory controller to fetch the instructions. It's going to tell the registers, it's like, here, give the program counter to the memory controller, and the memory controller is going to fetch the memory byte from that program counter, and then it's going to go get put on the data bus, where the decoder will figure out what to do from there, whether it has to fetch the additional operands after the opcode, and then once it has the full instruction, will then tell the registers and the ALU how everything's supposed to be routed, and then ultimately get written into a register or back out to memory, setting the status flags. All that stuff is going to be determined by that instruction decoder. And it's not going to be more of a modern thing where it's like a microcode type situation, at least not at this point. I'm not thinking you're doing that. I'm trying to make it take up as little space as possible. So it's going to be a very bespoke logic arrangement for decoding those instructions. I structured the instruction set just so that it could be decoded very quickly, and without having to go through this whole big microcode table to figure out what it's going to do. And so that's pretty much how it's going to be structured. And of course, I'm leaving a lot of detail. I even have details in the current documentation about how the instruction decoder interfaces with the memory controller. None of that's shown on here. When we get into a more detailed design, we're going to see all of the internal and external pins that are going to be dealt with for this design. But now let's just take a close look at the registers, because things have changed a bit since my last video. I've introduced a couple new registers, as you'll see here. But again, as a review, we have the A, B, and C registers. Those are each 8 bits. And you can see here, though all 3 of those can be demuxed into the left and right operands for the ALU. But then B and C can be considered a single 16-bit address register, and then that can be demuxed up to the address input for the memory controller, as ours we've seen before, the program counter PC and the stack pointer SP. But you'll see now there's a DD also providing an address to the memory controller, and that's one of the new some of the new instructions that I've added take advantage of this DD register for dealing with address. And this is going to allow us to have in registers 2 different addresses at the same time for doing memory copying, because again, that's something that you have to do a lot in these simple systems, because you're not necessarily going to depend on there being any sort of DMA controller or any other sort of special memory handling operation, cache scheme, any of that. It needs to be as simple as possible, so that somebody can create a really simple system and then have the instructions that are available to make it still perform reasonably well. So that's what the DD register is going to let us do, and we'll see how that works a little bit in this video, but later on in others we'll see some more concrete examples. And then we have the EE register, which is not an address register, but it is 16 bits, and that is going to be a counter. That's a 16-bit counter, because basically all you can do is load it with a value, and then you can increment it and decrement it. And then, when you're doing that, you can decrement it down to 0, and that will set off the 0 flag. So you can branch based on decrementing the 16-bit value. And that's pretty much all it's for. But it's an extremely useful thing, something that you're going to want to do a lot. And it doesn't take up a lot of space in the design or the instruction set, so it's an easy thing to just kind of stick in there. And of course, also you see at the far end the P register. That's just all the status flags, and it's actually not even 8 bits. It's really just 6 bits, but I put it in there anyway, because again, the whole register unit will be able to effectively put the value of the P register onto the data bus, just like it can all of the other registers. And that's of course for pushing it onto the stack and pulling it back off the stack and so forth. So that's what we're going to have for registers. And that's all I got really for slides. What I really want to show you now is the GitHub repo, and that of course is linked in the description, but its name of the repo is ROCKET88. And I've got here this documentation that I've started, and you can see I've got a little more detailed information if you want to read about it, about these different units and how they interact with each other, how the instruction set architecture works. A lot of stuff I had in that spreadsheet, sort of filling that out. And again, things have changed a little bit, but explaining how the different addressing modes work, what the different status flags mean. And then finally here, this opcode table, which will show us what it's supposed to be. Oh, did I not All right. I don't think I had refreshed this. Yeah, so you can see the internal components that are in there. We have that same diagram from the slides are all in there. And yeah, all the instruction sets. And finally, you get to the opcode table. And here, I think it also kind of illustrates the orthogonality of the instruction set, which just means that things are arranged in a way that it's going to be easy to decode an opcode. So you can see here, the columns here, this is the lower nibble of the opcode, and here's the upper nibble. So no op is at 0, 0. Load A with the B register is at hex 1, 2, and so on all the way down. Well, we don't have a XFF, but FE is decrementing the BC register. So you notice here we have 16-bit decrement and increment for the BC register, just like we do for some of these other registers like DD and EE. And again, that goes into the our means of being able to do large-scale memory copying, because we have these exchange methods. We can load a value into BC and then exchange that with DD or EE, and then mess around with it from there. But we also have direct loads and stores, indirect with the DD register. So we can store a value, an 8-bit value, to that memory address that DD is at, or we can then use the memory address in DD to load an A. And of course, we've already seen the same things with load A and store A, doing the same thing with the BC register. So we're going to load from one and store to the other, and that's how you're going to do this faster memory copy. So yeah, that's pretty much where we're at. And down at the very bottom is a bit of a preview of what's to come in the ROCKET88 repo. Of course, we're going to have this documentation that's already being developed. Like if you look at one of the load instructions, it'll bring up the load documentation, and it goes into great detail how all the different load instructions work. And it has little code examples in it, and that will get you an idea of what the assembly language is going to look like and how the machine code from that assembly language is going to be structured. But we'll also have in this repo the Verilog code for the core, and then also the emulator core, which is going to be in probably C or C++, maybe even Python. I might do a couple different languages, depending on what I feel like doing. And then that is going to be made as a library that you could then import into another like computer emulator. So I'll probably have separate repos for the complete computer on a chip, the FPG, a single FPGA computer for an FPGA development board like the one I've had in my other videos, or perhaps for, say, the DE10 Nano, like you see in the Mister. I think it'd be really cool to have a Mister core using ROCKET88, and that's definitely something I'm going to work towards. So I'll have different repos for different development targets, and certainly not thinking about any sort of custom board at this point. The big thing that I want to be able to do is for certain FPGA development boards, the certain popular ones, to have a single board computer program that can be put onto that, and it's running the ROCKET88 architecture. And then be able to take that computer architecture, and they're all going to be probably pretty much the same, but in terms of the initial version of that is not necessarily going to have any sort of graphics. It's just going to do everything through the serial port. and just work as a terminal, like the original computers used to do. You just had a simple serial terminal connection, and that's how you actually interact with the computer. And that's what the initial emulator is going to be. So it will have this core that will be found in this repo, and then another repo to have the actual emulator itself that will incorporate that core. And that's it. That's what I have planned for this. So I hope you stick with this series as I continue the development for this fun little processor. And I hope you're also just checking out some of the other stuff I got on the channel, especially my podcast here, Retro Brewhouse. And if you go here to retrobrewhouse.com, you're going to find all the episodes. We got 3 episodes so far. The first one is just sort of an introductory one, lets you know what we want to do with the podcast, that it's all about retro homebrew development. And it's other folks like me who are developing games and other technology around retro hardware, both modern retro systems like the Commander X16 and legacy systems like the Atari 2600 and the Commodore 64, and each of which we have devoted an episode to so far. And our next episode is going to be about another retro platform. And that is to be determined at this point. It might be, I know we're definitely going to do the Nintendo Entertainment System. We're going to do the ZX Spectrum. We're going to do the original IBM PC. We're going to do Amiga. We're going to do a lot of these old platforms and talk about how we create new software, especially games and demos for them using modern tools, just like you see on my channel. But it's a bunch of other guys that are all into that same sort of thing. If that's the thing you're interested in, either it's your current hobby or something that you want to get into, check it out. You basically go to any podcast provider that you like, whatever app you currently use, and just search for Retro Brewhouse. It'll be on there, or just go to retrobrewhouse.com. You can listen right on there, or you get links to all of these different providers. And Apple is there. It'll be on Apple too. They just don't link you to Apple on here if you're one of those Apple people. And that's it. I just want to just give a little plug for that, because not a lot of folks are really checking this out yet. It's still very much in its infancy, but I want to get people to check it out. And so if you like my videos, I think you're going to really like this podcast. And of course, the video versions of the podcast are already on my channel. Not as popular as my regular videos, my vlogs and things like this. It's not doing as well. So go check it out. There's even a little bit of a extra visual bonus material that you're going to see on the YouTube video version. So hey, watch it on video again after you've listened to it in your car when you drive to work, and just have a nice, relaxing conversation. So there's my little plug there. But the one more plug, of course, is for the people that really make all of this possible, are the patrons for this channel and my whole sad little empire of retro nonsense. And these are the folks right here that really make it possible for me to be able to host and produce and distribute a podcast that itself is doing nothing but losing money. But these folks help cover those bills, so I'm not going broke doing my hobby, which is creating this channel and creating games and demos and podcasts and videos and all that. So if you want to get a real inside look at what I'm doing, and get access to this content before it's made available to the public, and get access to additional content that you're not going to find on YouTube or in the podcasts, just come visit us on Patreon. That link's also in the description, and you can join the club and really get to hang out with all of these cool people and have a real impact on the things that I do, and really get my attention when we talk about maybe some interesting directions that ROCKET88 can go, or that some of my other tutorial videos can go. Anyway, that's all I got for you this time. This, of course, is as typical for Slithy Vlogs, is a very rambly, non-ending thing, but I'm going to end it here. So I hope to not be quite so long until the next episode. Just make sure you're subscribed, click that bell to be notified, and you'll know when that next episode comes out. And don't forget to like the video and comment. And let me know what you think. Maybe have some other ideas. Take a look at that repo and see if you have any suggestions. And that really helps drive the engagement and gets more people involved in this project, because this is going to be an open source project. It's for everybody. I want everybody to have the opportunity to contribute. All right, that's it. I promise. Okay, goodbye.